Suppose I asked you to differentiate this function here. Well, we're going to start by applying the power rule, which says we can multiply this power by the coefficient of this function here. So we're going to write this as 8 times 1 over 8. Then we're going to take that function that was being raised to the 8th power, and then we're going to decrement it. That is to say, we're going to raise it to the 7th power. So that's a power rule in action. But we can't then forget about the chain rule, which then says we are going to multiply this result by the derivative of our our inner function here. So we're going to multiply this by x cubed, the derivative of x cubed minus 5, which is 3x squared. Well, if we clean this up over here, we see that this 8 is going to divide out with this 8, and we'll have just simply 3x squared times x cubed minus 5, all of this to the 7th power. And really emphasizing here that we were employing the chain rule along with the power rule. This kind of, let me do this in a separate color here, the power rule. Now, what if then I wanted to go in the reverse order? That is to say, I wanted to take this result that we have here and I wanted to integrate that. So if we are integrating this function then, or finding the antiderivative of this, it would then follow that if we are going in the reverse order, that I want to then do the opposite, but also find a way of making sure that I'm reversing that chain rule as well. And this process is often known as the reverse chain rule, or often called U-substitution. Why is it often called U-substitution? Well, the idea here is, let me actually leave this here. The idea here is that we're trying to think of a way to rewrite our integrand such that we can see some function, which we'll just somewhat arbitrarily call u. There's no real good reason why we call it u. It could be any other variable. But the idea that we're rewriting our integrand in terms of some function u, that we can easily see the power rule being employed. We can reverse the power rule. But to ensure that the reverse of the chain rule is happening, the derivative of that function u has to be somewhere in that integrand. So let's look at, again, this particular case. So if we were just starting from this problem from scratch, so let me actually just move this up so we don't get too confused. I would say this would be a good candidate to be our u function here. And that is somewhat arbitrary, but there's actually a good reason why this one makes more sense than 3x squared. Oftentimes, you would want to use the more quote-unquote complicated function. So x cubed minus 5, we're raising that to the 7th power. There's a lot more going on with that function than there is with 3x squared. So this probably makes more sense here. So we can see here that we would think about this integral as being u being raised to the 7th power, which would, if we rewrite this in terms of u, just simply u to the 7th, for example, du, this would be a lot easier to integrate than all of this over here. It simplifies things. Now hold on. We can't just jump straight to saying that this is u to the 7th du. What about this 3x squared? Well, this is where the derivative of u then comes in. We would say that the derivative of u is equal to 3x squared dx. We're differentiating this function here with respect to x. So that 3x squared dx. Now here's the deal with that. This du must be in our integrand. 3x squared dx must be in here in order for us to have reversed the chain rule. If we go back to our original problem here, this 3x squared came as a result of employing or applying the chain rule. Therefore, it would follow then in this integral, in order to reverse the chain rule, that 3x squared has to be there so that we can finish integrating. That 3x squared, the derivative of u, has to be in there. So this works out pretty cleanly. We can actually rewrite this as, again, u to the 7th. So u to the 7th here, what I have there. And let me actually change the color here. And this 3x squared is our du. Well, if that's now the case, I can then rewrite this as the following. The integral of u to the 7th is u to the 8th over 8, which I'm now applying the power rule for integration. Okay, and then I can say plus c. And what is u? Let's substitute back in what u is equal to. X cubed minus 5 over 8 plus c. Or I could write this as 1 over 8 times x cubed minus 5 plus c. And if we were to think about differentiating this function here, well, what do you know? That's the original problem that I had started off with. Now, what about that plus c? Well, we know that that constant actually doesn't matter too much. In this case, we could find the derivative of any constant, and we would have still resulted in the same function here, because the derivative of any constant is 0. So this concept here is the idea of reversing the chain, or what we call U-substitution. So if we go back to our notes for today, I wanted to highlight a couple of specific rules for U-substitution, and most of them are what you would expect. The main idea here is that if we want to employ reverse substitution or U-substitution, or reverse chain rule or U-substitution, the idea here is that the derivative of our inner function u, or u prime dx, must be in that integrand. And in the instances where that derivative is not in the integrand, we either need to then introduce some type of scalar, or we need to redefine x in terms of u. So we'll do some examples of that. Let's start with this very first problem here. Let's start with number 1. Okay, so for number 1 here, I'm going to employ u substitution. Now, it's pretty clear here what our u needs to be. We would say that let u be equal to 3x, actually I don't need the parentheses, 3x minus 1. In which case du would be equal to 3 dx. Now, in order for us to integrate here, I can replace that 3x minus 1 and write it u to the 10th. But I can't quite write du just yet, because du is equal to 3 dx. So in order for me to rewrite dx as du, I'm going to need a value of 3 somewhere in my integrand, but it's not there. Well, fortunately for us, this is a pretty easy workaround. I can actually go ahead and multiply my integrand by 3. So I can put that there. Now you might be thinking, wait, I'm not allowed to just do that. I can't just multiply something by 3. Well, I would say, yes, we can, as long as we also multiply all of this by positive 1/3. Because if you multiply by 3 and then multiply by 1/3, or multiply by 3 and divide by 3, you're not really changing the value of the integrand. So now that is the case, I can say that 3 dx, here it is my du. So I can write this here. There's my du finally. And I can't forget about that 1/3. And I'm just going to move that 1/3 over to the outside. This is just a scalar property. I can move that there so I don't have to worry about it confusing me with my integration. And now I'm free to integrate. I can say the integral of u to the 10th is u to the 11th. All of that over 11. Don't forget about that 1/3. This plus c. And to finish this off, I'm going to go ahead and resubstitute my value of u back in. So I'd say 1/3 times 3x minus 1. Oops. 3x minus 1, all of that to the 11th power over 11. Clean that up a little bit. All of that plus c. Can't forget about that constant of integration. Okay? So this was a pretty easy workaround when all we had to do was introduce some type of scalar there. So let's try something else here. Let's just go ahead and try something a little bit more complicated. Suppose we did something like, well, let's see here. What would be a good one? Okay, how about this one over here? Let's try number 4. So for number 4 here, ask yourself what would make a good option for our u here. We would say u is equal to, I'm going to go with the denominator here. I'm going to treat u as my x to the 4th minus 1. Because 1 is a little bit busier, but 2, hopefully you can see it now. We can see clearly that the derivative of u, in this case, is equal to 4x cubed dx. So if that's the case, then now I can rewrite this as the integral of u raised to the negative 2 power times, so u again was x to the 4th minus 1, which is in the denominator, so I'm raising that to the negative 2 power, times du, which was just 4x cubed dx. This was all of this. So I can just write this as let me just write this du here. So that's the case. Now this is easy to integrate. This is going to be u to the negative 1 over negative 1, all of that plus c. And let's substitute what that u is equal to. X to the 4th minus 1 to the -1 over -1 plus c. And this is actually pretty easy to clean up, so I'll do that. We can then write this as -1 over x to the 4th minus 1 plus c. Okay, so I'll let you continue to work through some of these practice problems. But in the meantime, I want to actually switch gears a little bit and actually talk formally about U-substitution when it's absolutely necessary. So in the previous problems, you could have actually done all of these previous problems here without actually defining U. That is to say, if I wanted to jump straight from here to this, that's actually possible because we're really just reversing the chain. So you don't actually have to define any of our function in terms of U. And if that's easier for you to work through that, then by all means, go for it. But if we look at a problem like what we have here, this is where U-substitution actually becomes a necessity. So take a look at this practice problem here, and let's go through the steps. Let's determine which function we want to be our U here. So in this particular case, I want my U, what would be the busier function, or what looks like there's more going on? In this case, it would probably make more sense to have U be equal to x minus 1. In which case then, du, the derivative of U, is just 1 dx. Now, nothing that we've done so far is new. We've already worked through this. Now, if we were to try to rewrite these back in terms of the function, we would say we've got x times u to the square root of u, which I'll actually just write this as this, and then du. The problem is I've got this x that's just sitting there, chilling, and it's not going anywhere. And there is no way for me to introduce some type of scalar simply so that I could just easily integrate this using the power rule. So this is where I am going to jump to step number 4. If this is not in a form that we have a rule for integrating, we're now going to need to redefine x in terms of u. So going back to this now, move this over here. Going back to this now, I'm going to say, okay, well, if u is equal to x minus 1, that means that x is equal to u plus 1. And what this does is it allows me to rewrite x in terms of u. So now I can then say the integral of u plus 1 times u to the 1/2 du. And now this is something I can integrate. I can distribute my u to the 1/2 to write this as u to the 3/2 plus u to the 1/2 du, all of that du. And let me continue my work over here. Now I can apply the power rule to each term. So this is equal to u to the 5/2 divided by 5/2, which is simply multiplying by the reciprocal, plus u to the 3/2 times 2 over 3, all of that plus c. Looking at this over here, u then is equal to x minus 1. So we have 2 times x minus 1 to the 5/2 over 5, plus 2 times x minus 1 to the 3/2 over 3 plus c. Okay, so that should give you kind of a sense of how to approach some of these problems when we're working with U-substitution, when U-substitution becomes pretty much absolutely necessary, and in which cases we would just be able to, quote unquote, reverse the chain.